Jeśli sobie podniesie, tak, teraz się podłączyło. Marcinie, zamknij. Ja jeszcze nie. Może drugi Marcin zamknąć. Chciał sobie wziąć ciacho. Good afternoon. Today our speaker is Patryk Iwanek. Patryk started his adventure with astronomy in Magellanic University, but in 2015, after get bachelor there, he moved to Warsaw and started course with Professor Soszyński. He works on the magnetically active stars, and then he completed masters and start PhD here, and he will defend his thesis in the next month. Okay, Patryk, floor is yours.
Thank you, Mariusz, for introducing me. So today I would like to tell you about the scope of my PhD thesis, which I submitted roughly 4 months ago. So my PhD thesis, as you can see on the screen, concerns on analysis of Mira-Type stars, their variability, and using them as a standard candles to study the structure of the Milky Way. Let me start from the beginning. So a few words about Mira stars. Mira CET is historically the first identified variable stars, and the Mira CET becomes the prototype of a subgroup of high amplitude long period variables. Mira-type stars are asymptotic giant branch stars which pulsate in fundamental mode. These stars are at the end of their lives, just before the planetary nebula and white dwarf stages. Mira-type stars pulsate with periods from approximately 80 days to over 1000 days, and with brightness amplitude in optical bands larger than 2 magnitude, and brightness amplitude decreases with the wavelength. The luminosity of Miras ranging from several hundred to tens of thousands of the solar luminosity, while their average density is about 7 to 8 order of magnitude lower than the solar density. Usually Miras and other HB or RGB stars are divided to oxygen and carbon rich based on photometric or spectroscopic characteristics. Here you can see 4 examples of Miras light curves from the OGLE collection of variable stars. As you can see, the light curves is characterized by high amplitude pulsations. However, in Miras, we can also observe long-term changes in the mean magnitude, which is probably caused by the mass loss phenomenon. The main goal of the PhD project was to measure the distances to the galactic Miras and study the three-dimensional structure of the Milky Way. However, to achieve this goal, we had to face several problems. So first of all, we had to measure amplitudes for, we have to measure mean magnitudes for high amplitude stars. So the question is how to measure mean magnitudes for such high amplitude stars. The other problem is the extinction in the Milky Way, which is significant and can impact significantly stellar light. So the question was how to minimize the impact of the extinction. The other problem is that there were no precise period-luminosity relations for Miras, especially separately for oxygen-rich and carbon-rich stars. And the most important thing for studying the three-dimensional structure of the Milky Way, the large number of stars is required. To achieve the main goal, we performed a number analysis and we developed some methodology. All results have been published in 4 papers, which are logically connected, and they led to study the structure of the Milky Way. In the first paper, we analyzed variability in the wide range of wavelengths, and we measured precisely mean magnitude, Miras mean magnitudes. The second paper was devoted to analysis and calibration the Miras period-luminosity relations in several mid-infrared bands. These 2 papers based on Miras from the Large Magellanic Cloud. The other paper described the collection of almost 66,000 Miras discovered in the OGLE data in the Milky Way. And the last 4th paper presents analysis of the Milky Way structure based on the Miras stars. These 2 papers are based on the data from the Milky Way. All 4 papers combined optical and infrared data, which turned out to be crucial in this project. So we use observations in totally in 14 bands in the range from 0.5 to 25 microns. We use optical data from the OGLE survey, so we use I and V bands. We use near-infrared data from the VISTA infrared YJK survey of the Magellanic Cloud. So we use from this survey 3 bands, and we used in total 9 bands from the mid-infrared space telescope. So we used data from WISE and Spitzer space telescope. The mid-infrared observations are really important for analyzing Miras variability, and I can tell you why. So in 1928, Gerasimovich showed for the first time period-luminosity relations for the Miras in optical wavelengths. So basically, this period-luminosity relations showed by Gerasimovich look something like you can see in this picture. So the period-luminosity relations has positive slope. In 1981, Glass and Lloyd Evans showed for the first time near-infrared period-luminosity relations, and they showed that in near-infrared, the slope of period-luminosity relation is negative. So the conclusion was that the slope of period-luminosity relations changes with the wavelength and becomes negative from approximately 2 microns. So this effect you can see on this plot here. So here you can see color magnitude diagram in near-infrared and mid-infrared with log P color coded. So the bluest, the bluish points represent the shortest pulsation period, while the brownish points represent the longest pulsation period. And from this plot, you can see that there exist stars with the shortest and the longest pulsation periods with similar brightness. So this is why the Gerasimovich seen positive slope of the period-luminosity relation. While, as you can see, for the mid-infrared, there is clear division between brightness depending on pulsation periods. The other advantage of the mid-infrared observations is that the extinction is smaller in this wavelength. However, the weakness of this data is that we usually had a few epochs per light curve, so these light curves were sparsely covered. In this project, also the OGLE data were crucial because for Miras observed by the OGLE project, we have long time span for many stars. As you can see here, we have light curves with time span over 20 years. So these light curves were a perfect data set to make light curve templates, which I can show you in the next slides. In the first step, we analyze the Miras from the LMC, discovered by Igor Soszyński in 2009. Soszyński used photometric properties to divide Miras and semi-regular variables into oxygen and carbon rich. And this division you can see here. Soszyński plot Miras in Large Magellanic Cloud Miras in color diagram and Wesenheit diagram. And as you can see here, there are the Miras are grouped in two clusters. The one cluster here marked with blue points are pretty flat, and the other cluster bent to redder colors. So throughout this whole presentation, we adopt almost the same division. So blue points means oxygen-rich Miras, while carbon-rich Miras are marked with red points. So we started the analysis with making light curve templates. We used the all Miras from the Large Magellanic Cloud published by Soszyński with photometric division into oxygen and carbon rich. And we used model proposed by He et al. This model, in these four plots, model and the model components are marked with black solid lines, while red points here means the OGLE data, the true data. And Miras variability usually is complex and could be driven by three different mechanisms. So pulsation, mass loss phenomenon, and turbulence of convective cells. And He proposed a model which can be decomposed to low frequency trend, as you can see with solid line in this plot. Strictly periodic components caused by pulsations, which you can see here, and the stochastic component caused by turbulence of convective cells, which you can see in this plot. And the final model looks like here. So as you can see, the final model fits pretty well to the original OGLE data. Having this template, which we derived here, we were able to feed this template to mid and near-infrared data. In this plot, the mid and near-infrared data are marked with green, orange, and magenta points. So we fitted this template by shifting and scaling the template in magnitude and shifting the template in phase. And as you can see, even for the sparsely covered light curves like from Spitzer, where we had only 2 epochs, this template fits pretty good to the observations. Using the fitted and scaled templates, we measured amplitude ratios and phase lags between the wavelength and the OGLE I band, separately for oxygen-rich and carbon-rich Miras. Here, I show you only plots for carbon-rich Miras. So from this plot, you can clearly see that amplitude strongly depends from wavelength and decreases with wavelength. And the true measurements are marked here with red points. A similar picture can be obtained for phase shift. However, as you can see here, for carbon-rich Miras, the relations between phase shift and wavelength, I can say that it doesn't exist. The situation is slightly different for oxygen-rich Miras, where we can observe a small relations between wavelength and a weak relations between wavelength and phase shift. The interesting thing in this plot is this solid line and orange shade here. So we identified a subsample of 140 Miras with high quality and well-covered light curves in each band. And then we used templates for these light curves to obtain spectral energy distributions for them. And we, for each light curves, we obtained 6,000 SEDs per star. So we obtain one SED per star per day. And we fitted each SEDs with single or double Planck function. And we measured the amplitude ratio and phase lag in the range of wavelengths from 0.1 to 40 microns with step of 0.1 micron. Here you can see the example of the SED and the evolution of the SED in time. So the top plot presents one SED during one day of observations, fitted with double Planck function. Here you can see the evolution of the SED in time. So here we plotted 6,000 SEDs, which are color coded with the temperature, star temperature. This plot presents the evolution of temperature of the star, and here you can see the temperature of the dust, because for the carbon-rich Miras, most stars required the presence of the dust component in the model. And these relations marked here with solid line will be used further for proper estimation of the mean magnitudes in mid-infrared bands and their uncertainties. we made another use of the SEDs. So we generated synthetic light curves for each of these 140 stars. We generated synthetic light curves in 42 different bands from existing and future sky surveys. So we used bands which you can see, for which the transmission curves you can see here. So we generated light curves in Gaia, in WISE, but also in the planned LSST or recently launched JWST. And we measured the mean magnitudes and fitted the period-luminosity relations separately for oxygen-rich Miras and carbon-rich Miras in each of these bands. So here you can see 42 period-luminosity relations in this band which we analyzed. The plots, these two plots are ordered by wavelength. So in the top left plot, you can see the shortest wavelength, which is 0.47 0.37 microns, and this is band from the LSST U band. And the wavelength increases from left to right and from top to bottom. And as you can see, as I said, the slope is going to be negative around 2 microns, and also for longer wavelengths, we observe that the relation is going to be thinner. In the second step of this analysis, we used template slide curves to measure the mean magnitudes in mid-infrared bands. So we fitted in total period-luminosity relations in 8 bands, for Spitzer bands and for WISE bands, separately for oxygen and carbon-rich Miras. And we calibrated these period-luminosity relations on the distance to the Large Magellanic Cloud measured by Pietrzyński in 2019. Here you can see the example of period-luminosity relations, period-luminosity relation in WISE W1 bands for carbon-rich Miras. And as you can see here, this relation is linear. However, in the case of oxygen-rich Miras, we made 2 fits. The first one consists Miras with log P smaller than 2.6, as you can see here in this plot. However, while for the whole range of pulsation periods of oxygen-rich Miras, we used quadratic fit because we noticed that the relations for oxygen-rich Miras bends around log P to 2.6, 2.7. We also estimated that these relations allow us to measure the distances to individual oxygen-rich and carbon-rich Miras with the accuracy of approximately 5% for oxygen-rich Miras and approximately 12% for carbon-rich Miras. In the first step, we made a search for Miras in the Milky Way, using, of course, the OGLE data. In 2013, Soszyński published over 6,000, the catalog of over 6,000 Mira variables toward the galactic bulge. And they established boundary between the boundary in the brightness amplitude between semi-regular variables and Miras. And this boundary is established at 0.8 magnitude. So here, in this project, we also adopt the same boundary between these two classes. So here the most tedious task started as we choose the traditional method of classification of variable stars. So we used visual inspection of the light curves. So after some automatic cuts on the brightness amplitude or pulsation period, we left with almost 200,000 of stars, which we examined by eyes and classified. As a byproduct of this search, we found a few thousands of semi-regular variables, a few thousand stars with other variability types, for example, spotted stars, a few hundred long secondary period variables, and several microlensing events. And in this plot, you can see the difficulty of distinguish Miras from semi-regular variables, because as you can see here, there exist stars which switching between Miras and semi-regular variable type. And the amplitude changes from the range, as you can see here, 1.2 to 0.2 magnitude. Yes, so finally, we closed our search having almost 66,000 Miras in the Milky Way. Over 40,000 of them are located toward the galactic bulge, while over 25,000 were discovered toward the galactic disk fields. Over 47,000 of them turned out to be new discoveries. We estimated the completeness of our catalog to be at the level of 96%, and we estimate that purity of this catalog is really high. However, we are not able to estimate the number, the one number which can describe the purity. And the purity of this catalog is high because the probability of confusing Mira-type stars with other type of variable stars during the visual inspection is very low. However, such a misclassification can be made mostly around this boundary between semi-regular variables and Mira stars. And here you can see the whole sample of Miras plotted in the galactic coordinates. The gray area in this plot present the OGLE footprint. And here you can see some examples of light curves from this collection. So here you can see 3 light curves for Miras located toward the galactic bulge fields. The most in the top plot you can see the light curve with the longest time span and the densest coverage. So here you can see over 23 years of observations. And the bottom plot presents one example with the shortest time span. So as you can see here, here you can see just only two years of observations. And 3 other examples for Miras from the galactic bulge, from the galactic disk. And now we come to the last part of the analysis, which is, of course, the structure of the Milky Way. So having these relations between brightness amplitude and phase shifts, accurate period-luminosity relations, huge set of Miras in the Milky Way, and of course mid-infrared data for them. We measured distances and their uncertainties, and we examined 3-dimensional structure of the Milky Way. So here we want to achieve 3 goals. First of all, we want to measure distances to the galactic center, the angle of the bar, but also we want to check if the X-shaped structure exists or is visible in the Mira stars. Originally, the X-shaped structure was discovered in the split of red clump stars, which you can see here. This is the plot from Nataf et al. The authors showed that in the red clump stars, so in the stars from one population, the authors observed split in the brightness, as you can see here. A similar result was showed by McWilliam and Tsokali in the same year. So the other group also discovered the split in the red clump, as you can see here. And the conclusion about this split in the red clump stars was that so if we observe the same population of star, but the one cluster of this population is brighter and the other is fainter. So it means that probably one part of this population is closer to us and the other one is farther from us. This effect can be visible in the ZX projection of the Milky Way bulge. As you can see here, this is the plot from the McWilliam and Tsokali. And the question was, is this structure could be visible in the Mira variables? So we started this analysis from division the Milky Way Miras into oxygen and carbon-rich classes. We used the left plot presents division for Large Magellanic Cloud Miras, and the right plot presents this division for Milky Way Miras. Here we used the division made by Soshinsky in 2009. However, we used color period diagram using mid-infrared color from WISE bands. And as you can see here, the oxygen-rich Miras clumped around 0.25 W1 minus W2, while the carbon-rich Miras bends to the redder color. And when we plotted the same picture for the Milky Way Miras, we observed that one group of Miras is flat, around 0 or 0.25 W1 minus W2, but there exist a lot of stars which bend to the redder colors. So using this similarity, we divide Milky Way Miras into oxygen and carbon rich classes using Gaussian mixture models. And here you can see the final division of these Miras. And during our analysis of Milky Way structure, we want to focus on the central part of the Milky Way. So we limited our exploration space to the three-dimensional cuboid. And we fitted to the Miras distribution 49-parameter model proposed by Sormani in 2022, which contains also the X-shaped structure. However, we want to make this sample the most complete, so we excluded from the analysis the area of low completeness, for example, caused by high extinction. So here you can see again the distribution of these Miras plotted in galactic coordinates. All Miras are color-coded with the brightness in the OGLE I band. And as you can see here, near to the galactic plane, we can observe that Miras are fainter. So basically, we removed from the analysis all Miras which are inside this polygon plotted here with black solid line. We had to slightly modify the Sormani model. We added the bar angle and we changed the origin of the coordinate system. And after that, we fitted this model to the Mira-Type stars distribution in 3 dimensions, of course, taking into account distance uncertainties. And we measured 2 main parameters of the bar, so the distance to the galactic center and the angle of the bar. But what is more important, we showed that X-shaped structure exists in Mira-type stars because we indicated that strength and slope of the X-shape are significant and different from 0. And these 2 measurements are consistent with the literature. So, for example, Pietrukowicz using RR Lyrae stars showed that the angle of the bar is 21 degrees. To conclude my presentation, I would like to show you projection of the 3-dimensional map of the Milky Way. Here you can see the view from the above or the top view of the Milky Way. Miras are marked here with blue points. Those are oxygen-rich Miras, while red points present carbon-rich Miras. Classical Cepheids are marked with gray points. The sun is here marked with this orange circle, and the center of the galactic center with the angle of the bar is marked with this solid shape, black solid shape in the center. The other 2 projection you can see here. And that's all from me today. Thank you for your attention. I have presented here only a smart part of my work, so if you are interested in more details, you can take a look on these papers or contact me directly. Thank you very much.
Okay, do you have any question? Please.
There are quite a few Miras that change their period with the film stuff, or don't change their brightness, which is covering touching after or how many of them do you expect?
I don't know.
Those are like 10 only half of the
Period is at the top of the red giant branch. Miras are at the top of the giant branch.
But but there are quite a few that change their period.
I didn't analyze the period changes in Miras, so I don't know the answer to this question.
So that is a period.
I have to check this because I don't know. But I think that this is small. If something like this exists, I expect that it should be a small part of this sample.
Maybe the stars that you excluded from your team.
Maybe, but I excluded these stars because they are they are obscured by the extinction. That was the main cause. That was the main reason why I excluded these stars.
Okay, Martin.
How do you define your complete?
So the okay, I will go back to this slide. So basically, to estimate the completeness, we used the overlapping fields of the OGLE. So we used the overlapping OGLE fields to estimate the completeness. So basically, if we observed in the OGLE survey one Miras in two different chips, we checked how many of such stars we identified in two chips, and so that was the method.
But it means that, let's say, 96% of those stars seems to be Miras, or it seems something else?
No, we checked only these stars which we classified as Miras.
Okay. And it means, let's say, that you will find all Miras brighter than high magnitude or something.
So this completeness is related to the OGLE brightness limit. So I think it is between Igor, you can help me, between 13 magnitudes to 20, 21 or something like that.
Okay, so you find 96%
in this brightness limit. Yes.
Okay. More question? Yes, Pavel, please.
Could you compare your results of the design, the Milky Way Center, with the previous results based on the Mira star, and why your number is smaller than
it is
the best measured distance to the Milky Way?
Based on different measurements which used the Mira stars. So all results are agree with the uncertainty limits. However, this number 766, which we obtained, so when you look on the other measurements from the Miras, you can check that this measurement is agree with other measurements from Miras stars in the uncertainty limit. However, I agree that the value is pretty small. Comparing to, for example, other measurements from gravity or something like that. I think that the biggest influence on these measurements has extinction. But if the extinction has the influence on this measurement, the extinction cost only the shifting all stars farther away from us or closer to us, but this couldn't. Yeah, so I think that this is caused mostly by extinction.
Yes, please.
Could you go to the slide with the template slide there? Okay, so the second from the bottom plot.
That one?
Second. On the lower.
Second from the bottom, okay.
Yes. So I'm guessing it shows n plus L plus Q or something like that. It will be not strictly periodic signal that's shown. Like the shape of it changes and the mean value.
Yes, right. Mm-hmm.
Okay, so that was one question. And the other is you had like 3 or 4 coefficients for every star, in the how you shift the sorry, for every band, how you shift the magnetic scale, how you multiply out magnetic scale, and how you shift that.
It was pretty hard tasks. So
did you pick like 3 numbers for every star, or
we used two different or even 3 different methods. We can discuss about this after this seminar, because it was pretty hard and long exercise.
Okay, I don't know. Pavel?
How do we know that all Mira stars are fundamental?
We don't know this for 100%, I think. So when we search for periods, we check if each star has more than one significant period, and we didn't find more than one significant periods in these stars. But I think that this is not sure for 100% that Miras are fundamental mode, on the fundamental mode.
There are no period-luminosity relations for longer periods than you can see for Miras. It is the hint that this is the fundamental mode. If not, we should expect additional period-luminosity relations for the fundamental mode for longer periods. Also, the period ratios for semi-regular variables that agree with the hypothesis that Miras was taking the fundamental mode. There are arguments that we are practically sure that Miras are fundamental mode for treatment.
More questions? No, any online participant questions? So I don't see none. So in this case, thanks, Patryk, again.
Thank you for your time.
See you next week.
Thank you. Bye.